Okay, welcome back to part 2 video where we left off was finishing with box plots. So now we will continue working with bar graphs. So we know that bar graphs are used for categorical data and they assign the height of the bar or the count to each group. And visual comparisons, often easier than just looking at numbers, but sometimes simple is better. So keep in mind that maybe a table could be an option, but if we're deciding to go with a bar plot, then this is what we can do. So there's two different ways that we can create bar graphs in ggplot. We can either plot the raw data itself and then let the function do the binning, let the function work with the statistical transformation. Let it do the counting, or we can specify the count ourselves. So we're first going to learn the easier way by using geobar with the raw data. So by raw data, I mean that there is one row per observation. It isn't already grouped, it isn't already counted. And to do a bar graph, what we have to do is really easy. We just have to add geom_bar. And that gives us a bar graph for each of the different cuts. Super easy. Because it's doing that work behind the scenes for us. And right now it's based on count. So we've learned before that we can also have relative frequency histograms. But for now, let's learn how to create it based on summarized data. So if I already have that frequency table, if I already have that count information, one way that I can create the counts is by using a function called table. If I run this code, right, that really easily gives us the counts of each variable. But one thing to note is that all of ggplots are expecting data frames. So if I take a look at the class, this is a class table. So that's not going to work well with our ggplot function. Instead, what we're going to do is use a dplyr function, which is a function from a package that we're going to learn in the next tutorial, where we learn how to manipulate data, transform data. And what this does is count the information. So count the diamonds data set by cut and returns a data frame. So this is now in a format that works well with our ggplot. So now, in order to use this cut table as the data rather than the diamonds itself, what we have to do is two things. The first thing that we have to do is we have to specify the heights ourselves in the AES. So if you look at the output of the cut table, I have n as the heights. So my y is going to be equal to n. So my heights, the y is equal to my count. And the x is the groups, the cuts. And then what we have to do is, well, let's take a look at running this code. When I run this, it throws an error because this isn't the correct use of geom_bar. So what we have to do is we have to tell it to not do any counting. So we have to tell it to use this data directly and don't do any transformations. When I use stat equals identity in quotes, that gives me the same bar plot. But there's still yet another way to do it. So if I don't want to mess with having to specify the stat to use, the transformation to use, I can use the same setup as my cut and n as my aesthetics and switch to a different geom call, so geom column rather than geom_bar, and that gives us the same output as well. So 3 different ways to create the same bar plot, just depends on the type of data that you have and how you want to specify it. So there is an exercise for you to do. Try to look at the data before there's been some processing done to see what method you need to use to create this bar plot. So next up is displays for bivariate categorical data. So now we're working with a second categorical variable. And what we can do is use geom_bar, but now we're going to use color. We're going to color by a second variable. So let's add color equal to clarity and see the result. So we're going to just use the pre-processed, so it's going to do the binning for us. But notice again, right, color is the outline of the bars. So let's switch it to fill. Now what we have is a kind of stacked bar graph where the counts for the ideal are broken out by clarity, by the different colors. So we still get an idea of the total sample size of the group, but now we get a breakdown of a second variable. If we're more interested in the distributions within each rather than the total counts, we can use a proportionally stacked bar graph. And to do this, all we have to do is specify an argument within geom_bar. And that argument is going to be the position. So if we do position equals fill and run that code, that gives us now a proportionally stacked bar chart, which is better for looking at the distributions across categories. So we're not really concerned with total sample size now. We lose that information, but we're really looking at the conditional distribution. So within ideal, this percentage is I1. This percentage is S12. That's how we're reading a proportionally stacked bar graph, and we can compare that distribution across categories. But if we did want to get an idea of the sample size still, this kind of loses it. So what we can do is create a side-by-side bar graph by changing this position argument to Dodge. This will create a side-by-side bar graph. So now we get an idea of the breakdown within each by still having a good visual of the sample sizes as well. So a few different ways to visualize bivariate categorical data in another exercise for us. So next up is line plots. So a line plot is typically used when we're looking at a quantitative variable, so a numeric variable across time periods. And when this is the case, this is called a time series data. So the data that we're going to use is called the sunspot years, and some metric of the sunspots for each year. That is the data that we're working with, but we need it to be a data frame. So we've converted it to a data frame with 2 columns, year, 19 from 1700 to 1988, and then we are just grabbing the values from that. So this is our data frame. So to make a line plot, it's going to be super simple. All we have to do is add our variables that we need in the AES statement. So AES, X equals year, Y equals sunspots, based on my column up here. And then we can add geom line. And this should give us our line plot, time series plot. So super simple line plot for us. Next up is going to be facets. So this is going to be how we create different panels of distributions, different panels of graphs that are used to compare one distribution based on levels. So we're using those numerical distributions broken out by different levels. So rather than doing a comparative box plot, we're going to learn how to do a facet with, say, a histogram or scatter plots. So we have these distributions broken out by the levels of a different variable. The way we do that is with the function facet underscore wrap. And then what we have inside of this is the tilde, which is used to make a formula within R, and then the variable that is going to break out the different panels. So the only thing that we have to do is add that one line to our code. So first, we'll get a glimpse of all the data together. So this is all 50,000 points plotted together. But what we want to do is have a different panel for each different value of cut. So facet underscore wrap, the formula, and then the variable that we are grouping by. And when we run that code, that gives us a separate panel labeled based on the value. So that's how we can use facet wrap. And what it does is it just wraps, right? Facet wrap, it just wraps it in a rectangular fashion for each of the different levels. But let's say we have a particular type of plot and we want to control, either we want this to all be in a row or all be in a column. We can do that really easily using the n row and the n column arguments. So let's say I wanted these to be, let's take a look at what it is by default. So I want to look at this box plot, these box plots, but it's hard to look at it currently, right? I kind of have to go back and forth between the scales and they're not lined up properly. What would be easier is if these were all stacked vertically, then I can really easily compare, kind of like the comparative box plot setup earlier. We can do this with facets by using n column and setting it to one column. Now I have these all broken out by the different cuts, and we can really easily compare them across the same shared x-axis. But maybe for box plots, using a y aesthetic would be a better choice. But for histograms, we cannot use a y aesthetic, so that is when facets come into play. So let's take a look at this code. So now I'm making a histogram of the different prices for each clarity level. And we're going to have n row, so they're going to be in one row side by side. So take a look at this. 8 different levels of clarity and lots of histograms. This will be an example of overplotting. So even if I were to change this to n columns and stack these vertically, still not going to be a good graph. But nonetheless, it can be done. So let's take a look at the scales. So when I have the facet wrap, notice the scales of the different panes. They're all the exact same by default. So that has to go really high to get the ideal counts, but then it kind of zooms out way too much on the fair. We can change this behavior by using the scales argument. This allows us to set the scales, so that axis labels and the tick marks based on the data in that particular pane rather than the collective data as a whole. And there's a few different options that we have. So we have free X, meaning that the Y's will be the same across the panes, but the X's will change. Free Y, or both of them being free as just free. So if we want to correct this plot, we need to have free Y. So we're going to set scales equal to free Y. And when I run that code, now we have zoomed in the appropriate data pane. So that's how we can fix the scales on facets. There is another exercise. But let's say we wanted to facet by 2 categorical variables now. So I want to have a grid rather than just one factor. We can do that with facet underscore grid. And in our formula, we're going to have a 2-sided formula. So the first variable, which represents the rows, and the second variable, which represents the columns. So let's create our box plots, but faceted in a grid, and we're going to have each combination of cut and color. So right now I have 35 different box plots. So obviously this is a bit of overplotting. So just because we can do a plot doesn't mean that the plot is good. We can also fix the scales on facet_grid in the same way as facet_wrap. So there is an exercise for you to try as well. So next type of plot is going to be a density histogram and density curves. So as we saw, comparing numeric distributions for a categorical variable, multiple histograms or comparative box plots are a good option, but we might have to adjust the scales. If we're not really concerned about the counts, more the shape and the modality of that distribution, what we can do is make the heights proportional. In other words, make a density histogram. What that does is kind of standardize the heights. So each plot is going to have the same amount of ink. You can think of it like that. The way we do that is actually by specifying a Y aesthetic. So rather than by default plotting the counts, we are going to plot the after stat density. So we're not going to focus too much on how that works, but essentially after the ggplot does the transformation, we're going to pull the density values out of that and plot those on our Y. And when we do that, we don't have to have the scales argument. So we're kind of taking into account the scales by using the density rather than the count. So when I run this code, now we see that each one is kind of scaled appropriately, and we can see the modality now. We're not really focused on the sample size. So that is going to be a good option for us. And we can do this for just one histogram as well. So kind of extending that is going to be a density curve. So histograms are obviously really choppy, binned representations of that data. If we want more of a smooth curve, we can plot what are called density curves. And what that is we can think of it as kind of like a smooth curve, a blanket thrown over the top of that histogram. So with histograms, right, our best option is to change the number of bins, right? It's going to drastically change whether I have 30 versus 10 versus 50 bins. So it's going to change drastically, that visual based on that parameter. What a density curve does is kind of standardizes it. So it kind of is a more objective look at a distribution by looking at that smooth curve. So to create this smooth curve by itself, we need to use the function geom density. So let's go ahead and add geom_density. And that gives us that smooth curve by itself. So the exercise there is try to create a histogram and then overlay. So remember, each geom is an additional layer. So if we want multiple layers, we just have to add more layers. Simple enough. So now we can worry about multiple density curves. So this is going to be another way to visualize a quantitative variable by group. So broken out by groups. This is going to be often a better visual than multiple histograms. As we see, what we can do is just specify either the line type or the color. Typically, color will be a lot easier on us to read. So let's break out these density curves by the different cuts. now we have a different line for each value of cut. So this is a much better way to visualize multiple distributions on the same plot. Just be careful to not plot too many lines so that it doesn't get too jumbled. We can also make the lines a bit bolder by specifying the line width. So to make them stand out a little bit more, that is one thing that we could do to help. But notice that these histograms, or these density curves, right, they fit the data really, really well. So it's also kind of very particular in its spikes. It's matching it really closely. We can actually control that by a parameter called the adjust. And what that does is adjust the amount of smoothing that happens for that density curve. So larger values, such as 2, means that the probability is going to be more spread out. It's going to be a smoother curve. There's going to be less smoothing. Where smaller values like 0.2, it's going to be more sensitive. It's going to pick up on those smaller spikes. It's going to be more fine-tuned density curve. So let's see the difference between these ones. So if I do adjust equals 2, this is the amount of smoothing that's done compared to 0.2, where it gets really, really close. So it starts to look more and more like that histogram. As we smooth less and less, it gets more and more sensitive. So something to play with when you are creating density curves. So try that out in the exercise. So next up is the application. So your task is to recreate these visuals using the data set that has been provided. So BSU data BSU plot, if we run this code, that gives us the variables that we have. So we have the season, team, date, game number, and then if we scroll over, that gives us our points is somewhere along here. All of this different information, and we have the win-loss as the outcome and location as home. So there is no solution to this exercise, but see if you can recreate these plots and switch them from the first visual to the second visual. You'll know you can refer back to this if you get it right. So thanks for watching, and I will see you in the next video.